morning, good afternoon, good evening, whatever the case may be. We are back and better than ever, and today we are talking about Euler's form. Don't you ever say Euler, or you will be out quicker than you can say, I saw the sign by the great ace of base. Yes, get it? Because we're working with signs. All right, let's move forward. We'll come back to ace of base. This should be fairly quick. We are talking about Euler's form, or Euler's formula. The great Leonard Euler, proved that we can write the complex number mod z, or we've been calling it r, cis theta, can also be written in the form of z equals r e to the I theta. And to achieve this, he also proved that e to the I theta equals cosine theta plus I sine theta, which is useful to us. Okay, so if we have the complex number 1 plus I, we know that we can write it in polar form as root 2 cis pi over 4, and then using using Euler's form right here, we can write it as root 2 e to the I times pi over 4. We can't prove it. It's beyond the scope of this course. We have studied calculus, but not enough of it to be able to prove it. I do have some proofs that I'll show you on the next page. On our formula sheet, this formula is somewhat buried. It doesn't explicitly say Euler's formula, but we can see here that e to the I theta is equal to cosine theta plus I sine theta. And of course, you can multiply that by anything, and in this case, it would be r or mod z. Okay, so the proofs are here. Complex integrals, which are beyond the scope of this course, and series expansion as well. If you want to dig into it, have at it. But for now, we're going to accept it. Okay, so we're going to use it to evaluate some expressions here. So e to the negative I pi over 4. Let's take a look and say that e to the I theta is equal to cosine theta plus I sine theta, or as we know it, cis theta. Okay, and what do we have here? Well, we have e to the negative I pi over 4. Yes? And theta is the argument, clearly. So this is going to be equal to cosine of negative pi over 4, and we're using the negative for the argument, negative pi over 4 plus I sine negative pi over 4, which is equivalent to, don't tell me you don't know what the cosine of negative pi over 4 is, or what the sine of negative pi over 4 is. Lie to me, because I don't want to know if you don't know it. So this would be root 2 over 2 minus I root 2 over 2. And there we have an evaluation of this by hand. Of course, you could always crank that into a calculator quite easily, and if you did, you would see that this is obviously equivalent to that. For b, I to the negative I, ooh, that's kind of weird. Let's take a look at that. Well, we know that I, the complex number I, is written in complex form, is equivalent to or equal to 0 plus I. Which is equivalent to, please tell me that you can write this using cis theta, which would be cosine of our argument. Think about it. What's it going to be? My cosine is 0, my sine is 1. That must be pi over 2, boys and girls. So cosine pi over 2 plus I sine pi over 2. Say yes. It's a lot of stories. Baby, just say yes. Okay. So then that is equivalent to, by Euler's form, e to the I theta, or e to the I times pi over 2. That's a lot nicer and cleaner then, well, I don't know if it's cleaner than cis pi over 2, but it's, it's not too bad, e to the I pi over 2. So what about I to the negative I? Ooh, that's weird. I to the negative I would be equivalent to e to the I times pi over 2, yes, to the negative I, correct? And what does that do? Well, that is equal to e to the negative I squared pi over 2. Things are looking great now, correct? And I squared is equal to negative 1. And negative 1 times negative 1, last time I checked, was positive 1. So we end up with e to the pi over 2. Fairly nice. Hopefully it's straightforward, very simple, very easy. That's all I have. We just needed to be able to manipulate using Euler's form. So we will check back in with the legendary ASA base and see if they have found the sign, because I am out.